This is Chris Contalupo. I'm a developer of the GOPM software package, and in this video I'll be explaining uh, step 2 of our tutorial series. Please see the earlier tutorial series for more information about how to build and some of the uh, basics of how we defined our regions. So I'm currently in my current working directory is the tutorial subdirectory of the GOPM Git repository, and I currently have the tutorials built. And just to get started, before we go into what's in tutorial 2, I'd just like to start it executing. And we're going to do that as before, excuse me, um, by setting OpenMP numthreads to 16, running our defined MPI exec with 10 total ranks, with 4 for the application on each node. Okay, so while that's running, let's see how we've modified tutorial 1 to include the GOPM markup. And this will enable us to have reporting on each individual region of the code rather than the overall run as we have in the previous tutorial examples. So if you look at the source code for tutorial C, tutorial 2.c, you'll see that it differs at the beginning with this section where we define the GOPM region IDs. Also, we've included the GOPM header, gopm.h. You can see that we've declared these region IDs, one for each of the regions, as a uint64t, and these are populated when we call GOPM prof region, while specifying the name of the region, in this case tutorial sleep, stream, dgem, and alt-all. These strings are then hashed to this region ID, which is then set. You'll also notice that we provide policy hints for each of the regions. In the case of sleep, we provide the unknown hint. Stream, which is a memory-intensive computation, we provide the memory hint. Dgem, which is a compute-bound operation, we provide the compute hint. And for all-to-all, which is our network-bound application, we provide the network hint. As before, we have a loop. Runs over 10 iterations. But we've surrounded each of our regions now with a call to GOPM prof enter and GOPM prof exit while specifying the region ID that we derived above. So surrounding the tutorial sleep call, we have GOPM prof enter specifying the sleep region ID and the GOPM prof exit specifying the sleep region ID again. Similarly with stream, dgem, and all-to-all. You'll see that just before the call to all-to-all, there's an additional call to GOPM prof outer sync. And this interface is to be used just before a synchronizing call in your primary compute loop. There should just be one call to GOPM outer sync in your application, and it should happen just before blocking MPI call, such as all-to-all. So we've added that API as well, and the rest of the application looks the same as in tutorial 1. So again, we'll have reports here, and let's see what they look like. They are named after the tutorial. And you can see that, let's just look at one of them. Looking at the report from Mr. Fusion 1, you'll see a breakdown for each of the different regions. And they're named after their region ID that was specified in the call to GOPM prof region. You can see that, for instance, we spent 63 seconds in the stream region, 10 seconds in the sleep region, 40 seconds in the dgem region, and this node reported no discernible time in the all-to-all region. And then you'll see that there was time in this MPI sync. And what's important to note here is that because almost all of the work inside of this region was within the MPI function, that accounting has been placed inside of this MPI sync region, which is a special region that accumulates all MPI time. And then here, this is the outer sink region, and this is going to tell you the time for each transition through the loop. The total runtime being 120 seconds. That's the runtime for the entire application. That's what gets reported here in the special region. Likewise, this is the total energy used and the average frequency over the entire runtime. This count gives a count of the number of times the outer sink call was made, but this region refers to the entire application. And we'll have a similar report for the second node that we ran on. And again, you can see that the all-to-all has no time associated with it, but the time has been spent here in the MPI sync time. You also note that there's a 20 count for the MPI sync time, and that's because the all-to-all makes a call to GOPM, makes a call to MPI all-to-all, but it also makes a call to MPI barrier. So that's why this has a count of 20 rather than 10. Now, if we look in the trace file, you'll notice that there's something new to be seen now that we've added this markup. And though it can be difficult to see in a smaller screen, you'll note that this first column here is region ID. And in addition to the predefined regions, which you'll find in, this is the outer sink, for instance, there is also the regions that are associated with region IDs that we got back from the application. So if you run, for instance, the examples, there's an application called GOPM hash, and you pass the tutorial sleep. It will hash you the value for this string, and you'll notice that that's what's reported here in the first column while we're in the sleep region. And as we transition out of the sleep region into the stream region, we'll see that the hash will change to the sleep hash, which is, to the stream hash, which is here. It's this different number, and you'll find that in the first column of the trace when we transition. Okay, well, that concludes tutorial 2. If we look at the README, we'll find that next time in tutorial 3, we'll add some work imbalance to the application and show how the GOPM runtime can manipulate energy policy to undo the imbalance in the application. Okay, thanks for joining.